Hello friends, welcome back to my YouTube channel. This is part number 5 of my discussion on mass transfer coefficients, and in today's discussion I will be deriving relations between F-type and various K-type mass transfer coefficients. In part number 4 I had discussed different types of special K-type mass transfer coefficients. And earlier, I had discussed F-type mass transfer coefficients. I'm giving link to the entire playlist of my videos on mass transfer coefficients. So today, we will know relations between F-type mass transfer coefficient and various K-type mass transfer coefficients. Let us begin the discussion. To begin with, we will understand briefly about F-type mass transfer coefficient. I have made a separate video on F-type mass transfer coefficient. It is available in the playlist, for which I have given link in the description section. So F-type mass transfer coefficient, it is a parameter. It is a parameter that is used to describe the rate of mass transfer in turbulent diffusion in a manner similar to that in molecular diffusion. That is, we modify the equations for molecular diffusion by introducing a parameter. The parameter replaces a group in those equations for molecular diffusion. The group that characterizes molecular diffusion, it is replaced by a parameter that characterizes turbulent diffusion. So that parameter is nothing but the F-type mass transfer coefficient, a parameter used to describe the rate of mass transfer in turbulent diffusion in a manner similar to that in molecular diffusion. To understand this, let us consider a simple situation. Again, I had discussed it in detail in my video lecture on F-type mass transfer coefficient. So here I am considering a pool of stagnant water, and air is flowing past this pool of water under turbulent conditions. So as the air comes in contact with the water, water gets evaporated, and water vapor will then be diffusing through air which is under turbulent conditions. So you have the situation. So this is water which is stagnant. It is in contact with air under turbulent conditions. Water, I'm going to denote it by A. Air, I'm going to denote it by B. Then at the surface of water, there will be a thin film of air. And what is the significance of this air? Within this film, the conditions are stagnant. Although bulk of the air is under turbulent conditions, under turbulent flow, air within this film is stagnant. That means laminar conditions are prevailing within this layer. Therefore, molecular diffusion will be predominant in this layer. Whereas in bulk air, which is under turbulent conditions, turbulent diffusion will be predominant. So for our discussion, we are considering the direction of flow of air to be x direction, and the direction in which water vapor diffuses through air, we are going to consider it as z direction. Then we will consider a point on the surface where z is 0, and at that point, let the concentration of water vapor in air be Ca1. Ca1 is concentration of water vapor in air at the surface, and at any other point which is away from the surface, the concentration of water vapor in air is Ca2. So in this case, the mass transfer, what mass transfer is involved? There is transfer of water vapor, that is air, through water vapor, that is E, through air, which we are going to denote by B. So for this mass transfer, we need to understand that molecular diffusion is predominant in the laminar layer. Within the laminar layer, molecular diffusion is predominant, whereas as you move away from the surface and go into the turbulent zone, turbulent diffusion is predominant. So molecular diffusion is predominant in the laminar layer and turbulent diffusion is predominant in the turbulent zone. Let us move ahead. Now for molecular diffusion, the equation that gives us rate of mass transfer is this one. I had derived it in my discussion on F-type mass transfer coefficient. So the equation is Na is equal to dAbC upon Z into Na upon Na plus Nb into ln of Na upon Na plus Nb minus Ca2 upon C divided by Na upon Na plus Nb minus Ca1 upon C. So in this case, Na is molar flux of A relative to a fixed position in space. Nb is molar flux of B relative to a fixed position in space. Then Ca1 and Ca2, these are molar concentrations of A at point 1 and 2 in the previous diagram. Then dAb is the diffusion coefficient or diffusivity of A in B. Z is the length of the diffusion path between the 2 points, between point 1 and point 2. And C, capital C, is the total molar concentration. I have derived this equation in my video on F-type mass transfer coefficient. If you have not yet seen that video, you please watch it. So capital C is the total molar concentration. Now in this equation, the term, which term? dAbC upon Z. What is the significance of this term? This term is characteristic of molecular diffusion. So this term dAbC upon Z characterizes molecular diffusion. So this term, when you replace with a parameter that characterizes turbulent diffusion, then you can use this equation for finding rate of mass transfer in turbulent diffusion. And the parameter that is going to replace this group is nothing but the F-type mass transfer coefficient. Let us move ahead. So in order to use this equation, as I said, to use it for turbulent diffusion, the term dAbC upon Z is replaced with a parameter that characterizes turbulent conditions. And this parameter is nothing but F. This parameter is F, and that is the F-type mass transfer coefficient. It is a local mass transfer coefficient which will change on the surface of water. Therefore, for turbulent diffusion, what you can say, this equation now can be written in a new form. Na is equal to F into Na upon Na plus Nb into ln of Na upon Na plus Nb minus Ca2 upon C divided by Na upon Na plus Nb minus Ca1 by C. So you must have noticed we have replaced dAbC upon Z with F. Now you can use the equation which is similar to the equation that is used for molecular diffusion. But now it is in terms of F, the F-type mass transfer coefficient. So I hope the concept of F-type mass transfer coefficient is clear to you. If you have any doubts, you please mention them in the comment section. Let us move ahead. Then let us know in brief about special K-type mass transfer coefficients. Again, I have a separate video on special K-type mass transfer coefficient. It is part number 4 of my discussion on mass transfer coefficients. Over here, I have included a brief discussion on those special K-type mass transfer coefficients. So special K-type mass transfer coefficients, they are defined for two most frequently occurring situations in mass transfer operations. Which are these two most frequently occurring situations? One is A diffusing in non-diffusing B, and the other one is equimolar counter diffusion of A and B. These two situations occur frequently in the mass transfer operations. So that's why special K-type mass transfer coefficients, they are defined for these two situations. Now, for defining K-type mass transfer coefficients or for defining special K-type mass transfer coefficients, we use N-type molar flux rather than J-type molar flux because that is more convenient. So the defining equation would be molar flux is equal to mass transfer coefficient into concentration gradient. That is N type of molar flux for A is equal to mass transfer coefficient into concentration gradient. And since there are different ways of expressing concentration gradients, for each case, there is a different K-type mass transfer coefficient. So concentration gradient could be molar concentration difference, mole fraction difference, partial pressure difference. So for each case, you have a different K-type mass transfer coefficient. I have discussed this in detail in my previous video. You please watch it if you have not yet seen that. Let us move ahead. Now for the special K-type mass transfer coefficients for gases, let us know how they are defined. So for the case of gas A diffusing in non-diffusing gas B, we have Na is equal to Kc into Ca1 minus Ca2. So mass transfer coefficient is Kc, driving force is molar concentration difference. Then Na is equal to Ky into Ya1 minus Ya2. Driving force or concentration gradient is mole fraction difference, and the mass transfer coefficient is Ky. Then Na is equal to Kg into Pa1 minus Pa2. The driving force or concentration gradient is in terms of partial pressure difference, and in that case the K-type mass transfer coefficient is Kg. Then for equimolar counter diffusion of gas A and gas B, you have Na is equal to K dash C into Ca1 minus Ca2. So K dash C is the mass transfer coefficient when concentration gradient is molar concentration difference and there is equimolar counter diffusion of gas A and gas B. I have discussed all these relations in my previous video. Then you have Na is equal to K dash Y into Ya1 minus Ya2. Then Na is equal to K dash G into Pa1 minus Pa2. So each mass transfer coefficient is different. Kc, Ky, Kg, K dash C, K dash Y and K dash G. So for different concentration gradients and for different cases, you have different mass transfer coefficients. Similarly, we had defined special K-type mass transfer coefficients for liquids. Now let us know those defining equations. Okay, before that, let me tell you, at the end, we will be getting relation between F and Kc. We will be getting relation between F and Ky. Then we will be getting relation between F and Kg. We will be getting relation between F and Kc dash. We will be getting relation between F and K dash Y. And we will also be getting relation between F and K dash G. Let us move on. Then special K-type mass transfer coefficients for liquids. So liquid A, for the case of liquid A diffusing in non-diffusing liquid B, you have Na is equal to Kl into Ca1 minus Ca2. So Kl defined for liquid A diffusing in non-diffusing liquid B when the concentration gradient is in terms of molar concentration difference. Similarly, you have Na is equal to Kx into Xa1 minus Xa2, mole fraction difference. Then for equimolar counter diffusion of liquids A and B, you have Na is equal to K dash L into Ca1 minus Ca2, and then Na is equal to K dash X into Xa1 minus Xa2. So in this discussion, we are going to get relation between F and KL. We are going to get relation between F and Kx. We are going to get relation between F and K dash L. We are also going to get relation between F and K dash X. So in total, we are going to get 10 relations between F and different K-type mass transfer coefficients. Let us move ahead. Now first, let us discuss relation between F and Kc. So we know Kc is defined for gas A diffusing in non-diffusing gas B by this equation Na is equal to Kc into Ca1 minus Ca2. That is, Kc applies for this case when the driving force is molar concentration difference, and I am calling it as equation number 1. So for molecular diffusion of gas A in non-diffusing gas B, that is, if you have two planes separated by distance z, at this plane let Pa1 be the partial pressure of A and Pb1 be the partial pressure of B. At this plane let the partial pressure of A be Pa2 and that of B be Pb2. And then A is diffusing from this plane, from a plane of high concentration to a plane of low concentration. Then the equation applicable in this case is Na is equal to dAbP upon RTZ into 1 upon PBm into PA1 minus PA2. I'm calling this as equation number 2. So I have derived this equation in my discussion on molecular diffusion through gases. So you please do watch my playlist on molecular diffusion. So in my discussion on molecular diffusion through gases, I have derived this equation. In this discussion, I'm directly taking the equation. Why this equation? Because this equation is applicable for molecular diffusion of gas A in non-diffusing gas B. So ultimately, we are going to replace the group that characterizes molecular diffusion with F. And in this equation, PBM is PB2 minus PB1 upon ln of PB2 by PB1. Let us move ahead. So we have the defining equation for KCNA is equal to KC into CA1 minus CA2. That was equation 1. And then the equation applicable for molecular diffusion, Na is equal to DABP upon RTZ into 1 upon PBM into PA1 minus PA2. This is equation 2. Now, what we will do, according to if you apply ideal gas law for the entire gas mixture, it will be written in this form. PV is equal to nRT, where P is pressure, V is volume, N is total number of moles, that is moles of A plus moles of B, R is the gas constant, and T is the temperature. So from this I can write P upon RT is equal to N upon V, moles per unit volume. And moles per unit volume is nothing but total moles per unit volume. It is nothing but total molar concentration. That is, in equation number 2, P upon RT can be replaced with C. C is total molar concentration, moles per unit volume. So this is one thing. The other thing is, if you apply ideal gas law for A at 1, because I want to convert PA1 to CA1, so that I can compare the two equations. So for that, I will be using ideal gas law for E at 1. At 1, that is on the surface, if you remember the diagram. So the law will be PA1 into V, partial pressure of A at 1 into volume, that is equal to moles of A at 1 into R into T. That is PA1 upon RT is NA1 upon V. PA1 upon RT is equal to moles of A at 1 per unit volume, and that is nothing but molar concentration. So therefore PA1 upon RT is CA1, or PA1 is equal to CA1 into RT. So what is my objective? The objective is to replace PA1 in this equation with this term. Similarly, we will be applying ideal gas law for A at point 2. Let us do that. So till now we have got equation 1, then equation 2. C, total concentration, total concentration is P upon RT. So P upon RT in this equation we are going to replace with total molar concentration. Then we got equation for PA1 when we applied ideal gas law for E at 1. So PA1 is CA1 into RT. So therefore, now let us use ideal gas law for A at 2. So it will be PA2 into V is equal to NA2 into R into T. Partial pressure of A at 2 into volume is equal to moles of A at 2 into R into T. That is PA2 upon RT is Na2 upon V. And Na2 upon V is molar C8. So therefore Pa2 is equal to Ca2 into R2. So now I can replace Pa2 with Ca2 into RT in equation 1. So with this equation 2, now what I will be doing, I will be replacing P upon RT with C, Pa1 with Ca1 RT, and Pa2 with Ca2 RT. So if I do that, equation 2 will be Na is equal to DABC upon Z into 1 upon PBM into Ca1 into RT minus Ca2 into RT. So P upon RT is replaced with C, and Pa1 is replaced with Ca1 RT, and Pa2 is replaced with Ca2 RT. In the next step, I can take RT common, so it will be Na is equal to DABC upon Z into RT upon PBM into Ca1 minus Ca2. So now we got this equation previously, Na is equal to DABC upon Z into RT upon PBM into Ca1 minus Ca2. Now in order to use this equation for turbulent diffusion, I will have to replace this group. I will have to replace the group DABC upon Z with a parameter that will characterize the turbulent diffusion, and that parameter is nothing but F. So this equation becomes Na is equal to F into RT upon PBM into Ca1 minus Ca2, and now I am calling it as equation number 3. Now the task is, I will be comparing equation 3 with equation 1. So in equation 1 you have Na, Ca1 minus Ca2, Ca1 minus Ca2. So comparing equation 1 and 3, I get F into RT by PBM is equal to Kc. And the required relation can be obtained by rearranging it. So it will be F is equal to Kc into PBM by RT. So this is the relationship between F, the F-type mass transfer coefficient, and Kc, the K-type mass transfer coefficient, defined for the case of gas A diffusing in non-diffusing gas B when the concentration gradient is molar concentration difference. So I hope you must have understood how we got this relationship. If you have any doubts, you please mention them in the comment section. Now next, let us get relation between F and Ky. So for that, we should know that Ky is defined for gas A diffusing in non-diffusing gas B. It is defined by this equation, Na is equal to Ky into Ya1 minus Ya2. That is, it is defined when the driving force is molar concentration difference, mole fraction difference, when the driving force is mole fraction difference, and I am calling this as equation number 4. So for molecular diffusion of gas A in non-diffusing gas B, we have equation number 2, which was written previously. Na is equal to DAB P upon RTZ into 1 upon PBM into PA1 and PA2. I have talked about it. Now, we need to use ideal gas law for the gas mixture, because P upon RT we are going to replace with C. So P into V is equal to N into R into T. That is, P upon RT is equal to N upon V, but N upon V is C. So it is P upon RT is equal to C. And then from Dalton's law of partial pressures, partial pressure of A at 1, that is PA1 is mole fraction of A at 1, Ya1 into total pressure. Similarly, PA2 is equal to Ya2 into P. So we will be replacing PA1 and PA2 with Ya1 into P and Ya2 into P respectively. So equation 2, with this it will be Na is equal to DABC upon Z, P upon RT is replaced with C into 1 upon PBM, and PA1 is replaced with Ya1 into P minus Ya2 into P. Let us continue with this. So that is Na is equal to DAB into C upon Z, P is taken common. So it will be DABC upon Z into P upon PBM into Ya1 minus Ya2. Let us continue with this equation. So we have the defining equation for Ky, Na is equal to Ky into Ya1 minus Ya2, that is equation number 4. And we got this equation, Na is equal to DABC upon Z into P upon PBM into Ya1 minus Ya2. Now, in order to use it for turbulent diffusion, what we have to do? We have to replace the group DABC upon Z with F, the F-type mass transfer coefficient. So therefore, it will be Na is equal to F into P upon PBM into Ya1 minus Ya2. Let this be equation 5. And now I'm going to compare equation 4 and equation 5. So if I do that, I will be getting F into PBM, P upon PBM is equal to Ky. And from this, I will get the required relation. The required relation will be F is equal to Ky into PBM upon P. So this is the desired equation between F and Ky. So I hope you have understood how we got this equation. If you have any doubts, you please mention them in the comment section. Okay, now let us get relation between F and Kg. So for that, we should know Kg is defined for gas A diffusing in non-diffusing gas B by this equation. Na is equal to Kg into Pa1 minus Pa2. So the driving force is partial pressure difference. I am calling it as equation number 6. So for molecular diffusion of gas A in non-diffusing gas B, we know that equation 2 is applicable. What is that equation? Na is equal to dAb P upon RTZ into 1 upon PBM into PA1 minus PA2. Now, ideal gas law, in order to replace P upon RT. So, ideal gas law for the gas mixture is PV is equal to nRT. That is P upon RT is N upon V. N upon V is nothing but capital C. So, we will be replacing P upon RT with C. So, that gives us equation 2 as Na is equal to dAb C upon Z into 1 upon PBM into PA1 minus PA2. And in order to use this equation for turbulent diffusion, we need to replace the group dAbC upon Z with F. So, the group dAbC upon Z is replaced with F. So, you have Na is equal to F into 1 upon PBM into PA1 minus PA2. I am calling it as equation number 7. Let us continue with. So, we have equation 6, which is Na is equal to Kg into Pa1 minus Pa2, the defining equation for Kg. This is equation 6. And then we just got Na is equal to F into 1 upon PBM into Pa1 minus Pa2. That is equation number 7. So now we are going to compare equation 6 and 7. So this comparison gives F into 1 upon PBM is equal to Kg. And from that you can get the required relation as F is equal to PBM into Kg. So this is the relationship between F and Kg. So I hope you have understood how we got this. If you have any doubts, you please mention them in the comment section. Okay, now let us get relation between F and Kc dash. So for that we should know that Kc dash is defined for equimolar counter diffusion of gas A and gas B. Through this equation, Na is equal to Kc dash into Ca1 minus Ca2. I will call this as equation 8. So Kc dash is defined for this case when the driving force is molar concentration difference. So for molecular equimolar counter diffusion of gas A and gas B, we have this situation when you have two planes separated by a distance of Z. At plane, concentrations or partial pressures of A and B are Pa1 and Pb1, whereas at the other plane, the partial pressures are Pa2 and Pb2, and E diffuses in this way and B diffuses in the counter current direction. So for this situation, molar flux is given by this equation. Again, I have derived it in my discussion on molecular diffusion through gases. So the equation is Na is equal to dAb upon RTZ into Pa1 minus Pa2. I will call it as equation number 9. Now, again we need to use ideal gas law because Pa1 has to be converted to Ca1 and Pa2 has to be converted to Ca2. So for that we will have to apply ideal gas law for A at 1 and 2. So if you apply ideal gas law for A at 1, it will be Pa1 into V is equal to Na1 into R into T. Partial pressure of A at 1 into V, that is equal to moles of A at 1 into R into T. That is Pa1 upon RT is Na1 upon V. But Na1 upon V, moles of A upon per unit volume, is nothing but the molar concentration at 1. So this is therefore Pa1 upon RT is nothing but Ca1. That is Pa1 is Ca1 into RT. So the task is in equation number 9, we will be replacing Pa1 with Ca1 into RT. Now in the same way, we will apply ideal gas law for A at 2. So we have the defining equation for Kc dash. Na is equal to Kc dash into Ca1 minus Ca2, equation 8. And then for this case, for equimolar counter diffusion of gas A and gas B, the applicable equation is Na is equal to dAb upon RTZ into Pa1 minus Pa2. That is equation 9. We are going to replace Pa1 with Ca1 into RT, how I have just shown. Now let us do it for Pa2. So for that we need to apply ideal gas law for A at 2. So it is Pa2 into V is equal to Na2 into R into T. That is Pa2 upon RT is equal to Na2 upon V. But Na2 upon V is Ca2. So Pa2 will be equal to Ca2 into RT. So now Pa2 will be replaced with this term. So that's why if you use in equation 9, it will be Na is equal to dAb upon RTZ. into Ca1 RT minus Ca2 RT. You have replaced Pa1 and Pa2 with Ca1 RT and Ca2 RT respectively. So in the next step, RT will be taken out as common term. So it will be Na is equal to dAb RT upon RTZ into Ca1 minus Ca2. That is Na is equal to dAb upon Z into Ca1 minus Ca2, because RT gets cancelled. And in the next step, I will multiply with C and divide with C in order to get this group dAbC upon Z. So therefore, Na will be equal to dAbC upon Z into 1 upon C into Ca1 minus Ca2. And in order to use this equation, for turbulent diffusion, the group dAbC upon Z is to be replaced with F, the F-type mass transfer coefficient. So if we do that, it will be Na is equal to F into 1 upon C into Ca1 minus Ca2. And now I am going to call this as equation number 10. Let us continue. So we have equation 8, Na is equal to K dash C into Ca1 minus Ca2. And we just got equation 10, which is Na is equal to F into 1 by C into Ca1 minus C. Now we will compare equation 8 and equation 10. So if we do that, it will be F into 1 upon C is equal to K dash C. Therefore, the required relation in this case, it will be F into C, F is equal to C into K dash C. So that is the relationship between F and K dash C. Let us move ahead. Next is we will get relation between F and K dash Y. So for that we know that K dash Y is defined for equimolal counter diffusion of gas A and gas B, for which the equation is Na is equal to K dash Y into Ya1 minus Ya2. I am calling it as equation 11. The driving force is mole fraction difference. So for molecular diffusion, for molecular equimolal counter diffusion of gas A and gas B, the equation applicable is equation 9. What is that equation? Na is equal to dAb upon RTZ into Pa1 minus Pa2. Now we have to replace Pa1 with Ya1. So for that we need to use Dalton's law. So Dalton's law of partial pressure is Pa1 is Ya1 into P and Pa2 is Ya2 into P. Mole fraction into total pressure at 1. Mole fraction into total pressure at 2. So if we use this in equation 9, equation 9 will be Na is equal to dAb upon RTZ into Ya1 into P minus Ya2 into P. That is Na is equal to dAb P upon RTZ into Ya1 minus Ya2, and now I am calling it as equation 12. Now if we use ideal, now we need to replace P upon RT. So for that we will be using ideal gas law. Ideal gas law that is applicable to the entire gas mixture. So the law will be PV is equal to nRT, that is P upon RT is N upon V, but N upon V is total molar concentration. Therefore P upon RT is capital C. So the next task is in equation number 12, we are going to replace P upon RT with C in order to have dAv C upon Z term in that equation. Let us move ahead. So we have the equation Na is equal to K dash Y, Ya1 minus Ya2. That is equation number 11. And now the equation just we got is Na is equal to dAbP upon RTZ into Ya1 minus Ya2, which was equation number 12. Now we also had got the replacement for P upon RT, which is C. So P upon RT will be replaced with C. So equation 12 in that case becomes Na is equal to dAbC upon Z into Ya1 minus Ya2. And in order to use this equation for turbulent diffusion, we need to replace dAbC upon Z with F. So dAbC upon Z is to be replaced with F. So if we do that, it will be Na is equal to F into Ya1 minus Ya2, and I will call it as equation 13. Now next we will be comparing equation number 11 with equation number 13, and the comparison gives F is equal to K dash Y. So therefore the required relationship in this case is F is equal to K dash Y. So this is the relation between F and K dash Y. So I hope you have understood how we get this relationship. If you have any doubts, you please mention them in the comment section. Let us move ahead. Now let us get relation between F and K dash G. So for that we know K dash G is defined for equimolal counter diffusion of gas A and gas B, and it is given by this equation. Na is equal to K dash G, Pa1 minus Pa2, and I am going to call this as equation 14. So for molecular equimolar counter diffusion of gas A and gas B, the applicable equation is equation number 9, which is Na is equal to dAB upon RTZ into Pa1 minus Pa2. That is Na is equal to dAB P upon RTZ upon P. So in order to get P upon RT in this equation, I am multiplying with P. At the same time I'm dividing with P. So now according to P upon RT will be replaced with C. For that we need to use ideal gas law. So ideal gas law is PV is equal to nRT. That is P upon RT is N upon V. But N upon V is total concentration, total molar concentration. Therefore P upon RT is C. So Na will be equal to dAbC upon Z into 1 upon P into Pa1 minus Pa2. Let us continue with this equation. So we have the defining equation for K dash G. Na is equal to K dash G into Pa1 minus Pa2. Equation 14. We just got this equation. Na is equal to dAbC upon Z into 1 upon P, Pa1 minus Pa2. In order to use this equation for turbulent diffusion, we need to replace the group dAbC upon Z with F. dAbC upon Z is replaced with F. So therefore you have Na is equal to F upon P into Pa1 minus Pa2. This is equation 15. Now next task is we will be comparing equation 14 and equation 15. And if you do that, F upon P, it will be equal to dAbC upon Z. We have to compare it with equation 14. So in that case, F upon P will be equal to K dash G. The other terms on right hand and left hand side, they are similar in both the equations. So F upon P is K dash G. And you can rearrange this equation to get the required relationship. So the required relationship will be F is equal to K dash G into P. So this is the relationship between K dash G and F. Let us move ahead. Next, we will be getting relationship between F and KL. Now, we will be talking about liquids. So, KL is defined for liquid A diffusing in non-diffusing liquid B. The equation is Na is equal to KL into Ca1 minus Ca2. The driving force is molar concentration difference. I am calling it as equation 16. So for molecular diffusion of liquid A in non-diffusing liquid B, that means when you have two planes separated by a distance of Z, at one plane, the mole fractions are XA1, XB1, density of the solution at plane 1 is rho 1, and molecular weight of the solution at plane 1 is MW1. And at plane 2, XA2, XB2 are mole fractions of A and B. Rho 2 is the density of the solution and MW2 is molecular weight of the solution. So in case of liquids, as you move from this plane to the other plane, there is change in the concentration. In case of gases, it was considered to be constant, but in case of liquids, it changes, appreciably changes, and we need to take that into consideration. So again, the equation for molar flux of A diffusing from this plane to this plane, that was derived. I had derived it in my discussion on molecular diffusion through liquids. I am taking that equation directly in the discussion. So the equation is Na is equal to dAb upon Z into rho upon MW average into 1 upon XBM, XA1 minus XA2. I am calling it as equation 17. In equation 17, rho upon MW average is average of the ratio rho upon MW at the two planes. So rho upon MW average is rho 1 upon MW1 plus rho 2 upon MW2 divided by 2. Since rho upon MW is nothing but molar concentration, kg per meter cube divided by molecular weight is kilomole per meter cube, which is molar concentration. And since it is appreciably changing from one plane to the other plane, we are using the average value. So that's why you have rho upon MW average, which is average of the ratio at the two planes. And XBM in this case is XB2 minus XB1 upon ln of XB2 by XB1, which is the logarithmic average of XB1 and XB2. Let us continue with this. So we have the defining equation for KL. Na is equal to KL into Ca1 minus Ca2. That was equation 16. And for this case, Na is dAb for the case of liquid A diffusing in non-diffusing liquid B. The applicable equation is Na is equal to dAb upon Z into rho upon mW average into 1 upon xBm into x7 minus xa2. That is equation 17. Now x7 and xa2 are to be converted to Ca1 and Ca2. So how are you going to do that? Rho upon mW average in this case is concentration, the concentration, because rho upon mW average is molar concentration. So we will be replacing rho upon mW average with C, because density is kg per meter cube. Density is kg per meter cube and divided by molecular weight. So it will be kilomole per meter cube, which is nothing but the molar concentration. So that's why rho upon mW average is nothing but the molar concentration C. Let us continue with this. So if you use it in equation 17, it will be Na is equal to dAbC upon Z into 1 upon xBm into x7 minus xa2, till we have to convert x7 and xa2 to Ca1 and Ca2. So it will be Na is equal to dAbC upon Z into 1 upon xBm. But x7, that is mole fraction of A at 1, is moles of A at 1 divided by total moles. So that's why it will be Ca1 upon C. Similarly, xa2 will be equal to Ca2 upon C, individual moles upon total moles. So in the next step, C will come out. So it will be Na is equal to dAbC upon Z into 1 upon C into xBm into Ca1 minus Ca2. Now, in order to use this equation for turbulent diffusion, we need to replace this group. So dAbC upon Z is to be replaced with F. So if we do that, it will be Na is equal to F into 1 upon C into xBm into Ca1 minus Ca2. This is equation 18. We will continue with this. So Na is equal to F into 1 upon C into xBm into Ca1 minus Ca2. The equation 18 that we just got. We have equation 16. Now you can compare equation 16 with equation 18, and if we do that, it will be F upon C into xBm is equal to KL. Therefore, the required relationship in this case is F is equal to KL into C into xBm. So the relation between F and KL is C into xBm. Let us move ahead. Now, let us get relation between F and Kx. So, for that, we know that Kx is defined for liquid A diffusing in non-diffusing liquid B by this equation. Na is equal to Kx into x7 minus xa2. I will call it as equation number 19. So, in this case, the driving force is mole fraction difference. So, for molecular diffusion of liquid A in non-diffusing liquid B, we have equation 17, which is Na is equal to dAb upon Z into rho upon mW average into 1 upon xBm into x7 minus xa2. But we know that rho upon mW average is nothing but total molar concentration. So therefore it will be Na is equal to dAb upon Z into C into 1 upon xBm into x7 minus xa2. So in order to use this equation for turbulent diffusion, the group dAbC upon Z has to be replaced with F. So if we do that, it will be Na is equal to F upon xBm. dAbC upon Z is replaced with F. So this is F upon xBm into x7 minus xa2. Let this be equation 20. Now we will compare equation 19 with 20 next. Let us do that. So we are getting relation between F and Kx. So we have Na is equal to Kx into x7 minus xa2. That is equation 19. We got equation 20. Na is equal to F upon xBm into x7 minus xa2. That is equation 20. Now equation 19 and 20 will be compared, and if we do that, F upon xBm will be equal to Kx. And from this we can get the required relationship, which is F is equal to Kx into xBm. So that is the relation between F and Kx. Let us go ahead. Next, we will get relation between F and KL dash. KL dash is defined for equimolar counter diffusion of liquid A and B. So the defining equation is Na is equal to Kl dash into Ca1 minus Ca2. Let that be equation 21. Then for molecular equimolar counter diffusion of liquid A and liquid B, where you have liquid at plane 1, the concentrations are XA1, mole fractions are XA1, XB1, density is ρ1, molecular weight is MW1 at the other plane, mole fractions are XA2, XB2, density of the solution is ρ2 and molecular weight is MW2. And for this case, for diffusion of A, the equation for molar flux is Na is equal to dAB upon Z into rho upon MW average into XA1 minus XA2. I have derived it in my discussion on molecular diffusion through liquids. I am calling it as equation 22. Next is we will have to convert XA1 to Ca1 and XA2 to Ca2 so that we can compare. But we know first thing is rho upon MW average is nothing but total molar concentration. So therefore it is Na is equal to dAbC upon Z into XA1 minus XA2. So that is dAbC upon Z. XA1 is Ca1 upon C, individual modes upon total modes. XA2 is Ca2 upon C. So in the next step, Na will be equal to dAbC upon Z, and this C is taken common. So it is 1 upon C into Ca1 minus Ca2. We will continue with this. So we are getting relation between F and KL dash. So for KL dash, we have Na is equal to KL dash into Ca1 minus Ca2, equation 21. We just got Na is equal to dAbC upon Z into 1 upon C into Ca1 minus Ca2. In order to use this equation for turbulent diffusion, we need to replace dAbC upon Z with the F-type mass transfer coefficient F. So therefore it will be Na is equal to F upon C into Ca1 minus Ca2, and let this be equation 23. So now if you compare equation 21 and 23, what do you get? F upon C is equal to, or KL dash is equal to F upon C. And from this you can get the required relationship as F is equal to C into KL dash. So the relation between F and KL dash is this one. Let us continue with this. Let us continue further. Next, we will be getting relation between F and K dash X. K dash X is defined for equimolar counter diffusion of liquids A and B, and it is defined by this equation. Na is equal to K dash X is equal to XA1 minus XA2. Let this be equation 24. For molecular equimolar counter diffusion of liquid A and liquid B, we have this equation 22, which is Na is equal to dAb upon Z into rho upon MW average into XA1 minus XA2. But in this equation, rho upon MW average is nothing but the total molar concentration. So therefore Na will be equal to dAbC upon Z into XA1 minus XA2. And now we have XA1 and XA2. Now you can compare. But in order to use it for turbulent diffusion, the term dAbC upon Z, we will have to replace with F. So therefore it will be Na is equal to F into XA1 minus XA2. Equation 20. Again, we are discussing relation between F and K dash X. So we have the equation Na is equal to K dash X into XA1 minus XA2, equation 24. We got equation 25, which is Na is equal to F into XA1 minus XA2. Now you can compare equation 24 and 25. So the comparison gives K dash X is equal to F, and therefore the required relationship is nothing but F is equal to K dash X. So this is how F and K dash X are related with each other. Let us move ahead. So in this way, we got all the relationships. Now let us collect all those relations. First we will collect all relations for gases, and then we will collect all relations for liquids. So all relations for gases. For gas A diffusing in non-diffusing gas B, we have F is equal to Kc into ppm by RT. Then F is equal to Ky into ppm by P, and F is equal to ppm into Kg. That is, F is equal to Kc into PBM by RT is equal to Ky into PBM by P is equal to PBM into Kg. So this is how different K-type mass transfer coefficients are related with F. And then for equimolar counter diffusion of gas A and gas B, you have F is equal to C into K dash C, F is equal to K dash Y, F is equal to K dash G into P. That is, F is equal to C into K dash C, that is equal to K dash Y, that is equal to K dash G into P. So overall relation, all relations are F is equal to Kc into PBM by RT, that is equal to Ky into PBM by P, that is equal to PBM into Kg, that is equal to C into K dash C, that is equal to K dash Y, that is equal to K dash G into P. So these are all relations for gases. Now let us look at all the relations for liquids. So all relations for liquids, for liquid A diffusing in non-diffusing liquid B, F is equal to KL into C into XBM, F is equal to KX into XBM, and therefore from this you can write F is equal to KL into C into XBM, that is equal to KX into XBM. Then for equimolar counter diffusion of liquids A and B, liquid A and liquid B, F is equal to C into K dash L and F is equal to K dash X. That is, F is equal to C into K dash L, that is equal to K dash X. So all relations will be finally you have F is equal to KL into C into XBM, that is equal to KX into XBM, that is equal to C into K dash L, that is equal to K dash X. So in this way, I have derived all the relations, or I have derived relation between F-type mass transfer coefficients and all of the special K-type mass transfer coefficients. So I hope you have understood the steps that I have followed in getting those relations. If you have any doubts, you please mention them in the comment section. Now for this discussion, I will, for this particular video lecture, I will end my discussion. So thanks for watching this video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day. Hope to see you soon in my next video lecture. In my next video lecture, I will be discussing the derivation of continuity equation, because that is required in the discussion on mass transfer coefficients in laminar flow. For now, have a nice day and hope to see you soon in my next video lecture.